with that definition or I guess, a high-level description from your perspective on the difference between motion control versus motion systems. We can certainly start with a traditional um, binary perspective.
Sure. So, I mean, motion control is going to cover the gamut of making a motion system move and instructing it what to do and how to work with other machines and uh, and at the lower level, it's just how does a device move in terms of the higher level integration of the amplifier that moves the motor and the control that tells the amplifier what to do. So, um, motion systems for us uh, are usually a conglomeration of our standard single axis products put into multi-axis subsystems that become a drop into a larger system for an OEM or an integrator.
Okay, so then my first question there, following that, is how has the balance shifted between that mechanical system design and control sophistication? Perhaps we can look back over 10 years and see whether there has been a change or not. And how has that affected how you at Val Everman design actuator platforms?
So the really higher level control system design that you might find on a semiconductor stepper system or higher level lithography machines and things like that, those are in the rarefied air of control systems where the control is really designed around the dynamics of the system. So it it's very different from the type of automation that we do, which is general automation, pick and place, metrology, motion. Um, you know, you can call our stages actuators, and they are everything that has to move something from A to B as an actuator. But the distinction between actuator and stage is usually fidelity. An actuator is going to do a kind of a blunt force motion of a device or product, and a stage is expected to move it more precisely. I would say that our involvement with control system design is less than our involvement with multi-axis motion in packaging and biomedical and aerospace and semiconductor.
You can answer both from an industry, your perspective on the industry, as well as specifically at Bell Everman. So as motion control architectures grow more software centric and they're becoming more networked, what new expectations do they place on the mechanical side?
I think it's made things simpler. I mean, the introduction of EtherCAT and these other protocols that allow large scale, large numbers of axes in a system. Um, it's just become simpler. They're networked. There's a great advantage to cable reduction and things like that when you can daisy chain axes and a lot of the motion control vendors, Rockwell and Bosch and Siemens, everybody now has their kind of distributed control architectures. And then at the lower level, there's the smart motors and things like that some of them are too smart in my opinion. They can do too much, and you don't end up using a measurable percentage of their capability. All you really want in most cases are to send a signal and it does a thing, and it's a very simple thing, like when we're replacing hydraulics and pneumatics. It's so much easier to have these types of distributed, smart motors, but there's also less smart ones that are more appropriate for the task of taking over the job of a pneumatic system. So um, it's it, it's very interesting. It's become transformative in making systems that do fairly complex things with with less. So, I would say yes, it's becoming software centric and a lot more software driven. And at the same time, we're getting tools that make it so that we can put together systems with very simple discrete elements in ways like they would have 50 years ago or 100 years ago with CAMs and making very special purpose motion systems that repeatedly in a manufacturing process do things over and over again. Like back then it would be, you'd make this huge machine with all these cams and it would make one part all day long, all night long. We need more configurability than that, but I would say 80% of the time we're making a machine that's going to do one thing and one thing only, and the customer wants to do it for 10 years and they want to know how few times they need to maintain it.
Oh, no, for sure. So I want you to talk now a little bit about, where the next meaningful gains, perhaps in performance, is coming from. So my question to you is, which industries are pushing the limits of motion systems performance today, and how are their requirements or their demands influencing actuator and transmission design?
Mm-hmm. Um, I would say the most brutal environment is food. Uh, the requirements just for being sanitary and physically geometrically not having any nooks and crannies that food can get in and rot and things like that. Being able to be washed down, that stuff like that. It is the worst problem to go after. And it ends up being a lot of times pneumatics, just because it's so easy to seal those devices. They're already sealed by their nature. You just have to make them out of stainless steel to be a food tool. And metrology, I would say, at the other end is what's driving these much more difficult problems for motion and for metrology and for controls. And all of the manufacturing of integrated circuits and semiconductors they're always looking to go faster and faster and faster, and that really does drive some really higher end control architectures where you have analog systems and extremely tight servo loops. And those are things that are becoming more common at the lower level of automation. We're able to use much higher fidelity um, um, servo loops than we used to be able to. And they're just becoming more prevalent. It's going to be a lot about UAVs and autonomous vehicles, which isn't a super difficult problem, but from the software side, it's much bigger problem getting them all to work together and collision detection and bringing AI into the mix for trajectory planning and things like that.
Yeah, no, indeed. The other thing that struck me as I go to various trade shows and look at, components, um, uh, the question is, are OEMs and machine builders increasingly favoring integrated motion subsystems over assembling discrete components? What's
Absolutely.
happening?
Absolutely. They don't they don't want to dedicate an engineer to put two axes together if they can have Bell Everman put together two axes for them, where they're just handling the higher level of control on that. And that's 80% of the work that we do is not including controls. We'll draw the line at the motor and sometimes the amplifiers. It's kind of a business model for us, this concept of land and expand. It makes a lot of sense when a customer comes to us for a single axis. We're looking at what other axes are involved or even connected to this axis, and can we fill that need? And it is a trend that they want to write fewer purchase orders. So we find that this is a very easy sell for us to add axes and even add the elements that go above and below but are attached to our subsystem. We will make uh, that content as a build to print And a lot of companies they're just all about that. They love the ability to get us to warranty a larger chunk. Um, and this is a pitch that goes over very well. Just say this is a subsystem. It's completely quality checked. It works right when you put it in. It will be the same as the last one and the last one and the last one.
Okay, one more question to stretch your mind in a different direction. Let's look ahead. Where do you see the next major inflection point in motion technology coming from? Would you say you don't have to stick to my list, but tell me where we're going. Are we looking at better advances in control intelligence,
Yeah.
mechanical innovation? Um, and certainly, I think, this is what I think, I'll have you tell me, tighter mechatronic integration for sure.
Uh-huh.
Am I right?
Uh-huh. Absolutely. And I think that anybody wants to try and fit AI in a sentence these days, but it truly is going to be transformative as it scales into microcontrollers and smaller systems that may not have connectivity to a larger data field. So I think that in the same way that 3D printers transformed mechanical design for us, 15 years ago, AI is going to transform things for us in motion control as well as engineering and design. Like I use it every single day in engineering to help me just to do the heavy lifting on justifying a plan or I don't want to derive equations anymore for specific things. I ask for the answer and it gives me the equations. And if I didn't know how to read those equations, I can't cut the cards on it. So you must know what you're looking at because I do end up correcting it occasionally, and it's mainly the assumptions that it has inferred that get balled up. But I think that in the future, um, AI is going to make it way down to the microcontroller level, and you're going to start having simple systems that decide whether it's actually okay to move. Is this thing that just came in to my purview actually right? Should I actually touch it or should I stop the line? And I think that that stuff as well is going to be more distributed than it is now. Now it's centralized and in a much larger processor. But I think all of these types of models are going to pare down to being able to make decisions at a finer, more granular level.
Wonderful. I couldn't thank you enough. Your insights are invaluable. Michael Everton, thank you so much for being with me today. It's been a pleasure.